In this video, we're going to briefly introduce limits by showing you some examples first of limits that exist and later examples of limits that don't exist. So let's start with limits that do exist. The first example is a polynomial, and we're taking the limit as x goes to 2 of f of x. So all we do is substitute in. Nothing unusual is going on near x equal 2, and in general, when we take the limit as x approaches anything of a polynomial, you just substitute in. So that's what we're going to do here. So here just substitute 2 in for x, because we're taking the limit as x goes to 2, so just substitute in 2. And we have 3 times 4, that's 12 minus 4 plus 1. Okay, that's 8 plus 1, so the limit is 9. So here the limit is the same thing as f of 2 in this case. The second example is similar. Here we're going to take the limit as x goes to 2 of this function. And this rational function, nothing unusual is going on near x equal 2. All right. This function doesn't exist at x equal 5 because of the x minus 5 in the denominator. But at x equal 2, the function does exist. All right, so let's just take the limit as x goes to 2, and if we have a rational function, and 2 is not a 0 of the denominator, then we take the limit as x goes to 2 by just substituting in, just like we did for the polynomial above. So here again, we're just going to substitute in. All right, so in the numerator there we have 4 plus 3 over negative 3, so that's 7 over negative 3. Again, the limit was gotten by substituting in, and the limit is the same as f of 2. Here's our next example of limits that exist. So we have a piecewise defined function. F of x is equal to the line 2x plus 1 when x is not equal to 2, and f of x is equal to 6 when x is equal to 2. Here's a picture of f of x. Here's the line y equal to 2x plus 1 with this 1 point removed. The point 25 is removed. Okay, so that one's removed. And the point 26 is on the curve. So in this case, f of 2 is equal to 6 because of this second line over here. So what about the limit as x goes to 2? Well, for the limit, we just substitute into this polynomial. Let's call this p of x, 2x plus 1. So the limit is not f of 2, the limit is actually p of 2. The limit is 5. From the picture we see when x approaches 2 from either side, the function's going up towards, on the left it'll be going up towards height 5, and on the right coming down towards height 5 when x approaches 2. So it makes sense that the limit should be 5. And we have a basic limit rule that says that if f of x is equal to a polynomial except at a point, then we take the limit by substituting into that polynomial. And here's the rule that we used for that previous example. The next example is a rational function, and we're taking the limit as x goes to 2. But notice that we have x minus 2 in the denominator, so the denominator is 0 as x approaches 2. But we can reduce the rational function first, so let's do that. And we reduce by, we'll factor that numerator into x plus 2 times x minus 2. And then cancel the x minus 2 from the numerator and denominator. So now we're doing the limit as x goes to 2 of x plus 2, and we can just substitute in. We eliminated the x minus 2, the problem, from the denominator, so we just substitute in. And here's the rule that we just used. Reduce a rational function if possible before taking the limit. So those 4 examples are typical examples of limits that do exist, and now we're going to do 3 examples. We'll see 3 typical examples of limits that do not exist. For our first example of a limit that does not exist, we're looking at a piecewise defined function, and it's defined as follows. To the left of 1, the function is equal to the line y equal x, and to the right of 1, the function is equal to the line y equal x plus 2. All right, so here we have, this is a piece of the line y equal x plus 2, and this is a piece of the line y equal x, and here's x equal 1. So if we want to take the limit as x goes to 1 of f of x, what we have to do is we have to break this up into 2 limits. Because of the way f of x is defined, we take the limit as x goes to 1 from the left, that's that little minus symbol indicates to the left, of f of x, and we take the limit as x goes to 1 from the right. All right, so here this is from the left, and that's from the right. So this one would be associated with that negative symbol, and this one with that little positive symbol, negative, positive. All right, so from the left, we're going to use this function, that is y equal x, and when we take the limit from the right, we're going to use this function, y equal x plus 2. All right, so let's just do that. So the limit as x goes to 1 from the left is obtained by just substituting into the top here, and we get just 1. All right, now let's do from the right. And we just substitute into this bottom function. So we have 1 plus 2, we get 3. And since these are not the same, we'll just indicate it like that they're not equal. Okay, so that implies the limit as x goes to 1 of f of x does not exist. Here's our next example, and it's really going to be similar, the same type as this previous example. So here f of x is equal to the absolute value of x minus 2 divided by x minus 2, and we want to know what is the limit as x goes to 2 of f of x. So first it's important to realize what this function is. Another way of writing it, and we saw this in class, is as follows. All right, let's do x greater than 2 first. And, oops. So we're starting with x greater than 2. So when x is greater than 2, the absolute value of x minus 2 is equal to x minus 2. So we're just going to get x minus 2 over x minus 2, and we have 1 over here. And when x is less than 2, the inside is negative. So we're going to end up with a negative 1 here. So this function is, if we graph it, it just looks like this. Here's 2. Okay, let's say here we have 1, and here we have on the y-axis, and here we have negative 1. When x is greater than 2, we have a straight line, horizontal line at height 1, and when x is less than 2, we have a horizontal line at height minus 1. x equal to is not in the domain. That's why I have two open circles here. That's because of the x minus 2 in the denominator. So the limit as x goes to 2 from the left, we're approaching from this way, from the left, we're down here at minus 1. And the limit as x goes to 2 from the right, we're approaching this way, and we're up here at positive 1. So again, these two are not equal. So we say the limit as x goes to 2 of f of x does not exist. The next example, f of x is equal to 1 over x minus 2, and we want to take the limit as x goes to 2 of f of x. So here's the graph. This function is has a vertical asymptote at x equal 2. On the left, to the right of 2, the function is going all the way up to infinity. And to the left of 2, the function is going down to minus infinity. So the limit as x goes to 2 does not exist. Soon we'll be talking about infinite limits, and we'll see that the limit from the right is infinity and the limit from the left is minus infinity. If the limit is infinite, it's considered a limit that does not exist, but we still will be talking about whether or not these limits go to infinity or minus infinity. So that summarizes the different types of limits, the different types of limits that exist, and the different types of limits that do not exist.